Now, we're going to take the ideas from the previous segment that are familiar to you from your course on ordinary differential equations and your course on linear algebra, and we're going to delve into territory that possibly you've never seen before. There will be some exercises for you to work through to try to fix the ideas in your thinking. But likely we're reaching the point here where you will need to take more advanced courses in the future in order to make complete sense of these ideas. Our notion of including this material in this special MOOC course is that you would see how the mathematical ideas fit and are needed to understand the more complicated aspects of the robot behaviors that we'll be discussing in future segments. In this segment, I'll be talking about just a pendulum, a simple pendulum hanging in the gravitational field. And we will be pretending that this pendulum is the leg, a 1 degree of freedom leg, a swinging leg with one joint of a body. If you prefer to think of it as an arm, that's fine, but we'd like to think about it as the simplest appendage. As you know, in most animals and in most robots that are interesting, there will be many, many, many more joints. Often there'll be revolute joints. And so you can begin to think about compound pendula when you start thinking of the many jointed robot arms and robot legs that we'll be discussing. These many jointed pendula have far more complicated behaviors than the simple 1 degree of freedom pendulum that I'll be discussing. But the idea and the mathematical connections are very, very much the same. And we will try to get that idea across by making the connection between this nonlinear 1 degree of freedom pendulum motion, which perhaps you've not seen before, in contrast to the 1 degree of freedom linear mass on a spring from the previous segment that you've seen before in physics and ODE theory. The first new idea that we'll be discussing at great length in a future segment on kinematics is the relative motion between constrained rigid bodies creates the nonlinearity. Because the pendulum swings around and around and around, the mass comes back to the same place that it's been, which would never be possible in the straight line motion of the original particle. This periodic phenomenon is characteristic of all the interesting kinematics. Revolute joints are much more useful in general than prismatic joints, as you'll come to see in our kinematic section. Yet they account for the origin of the nonlinearity. So let's look at the picture of the simple pendulum with point mass m at some position p. And I'd like you to think about p as having a spatial component. There's a position on the plane in the horizontal direction x and a position on the plane in the vertical direction z. And there's this fixed distance L, which the mass is constrained to travel on, thereby forming a circular arc whenever it travels at all. It can travel along that circular arc for many, many, many degrees, depending on how much energy it has. So our variable p, which looks like a planar variable, because it has two components, p sub x and p sub z, is really a 1 degree of freedom variable, but a nonlinear 1 degree of freedom variable, established by the kinematics of this simple pendulum. We'll model the geometric relation using polar coordinates, which you'll remember from high school probably. Namely, we'd like to think about the horizontal and the vertical components of this point mass p as having a radial component L, which is fixed, and an angular component theta. So that using trigonometry, we can express the position p sub x and p sub z, as the function g of the variable theta. Theta is a scalar variable, g is a vector. So g takes the scalar variable theta, the angle of the pendulum, and gives us back, reads out for us, the Cartesian positions, p sub x and p sub z, of the mass that's constrained to ride on that pendulum. G is a special function, and it's called the kinematic function, or the forward kinematics. And we think about it as mapping the joint space, that is the space of shaft angles, into the workspace, that is the space of positions. When we introduce the kinematics ideas later on in this MOOC, we will talk about kinematics at great length, but we will be increasingly less mathematical because the mathematics becomes very, very much more complicated. Here in this segment, we're still going to talk about the concepts in the mathematics in a unified manner, hoping that it will give you some insight later on when you study these more complicated kinematics at greater depth. So we will now add, having discussed the kinematics of the pendulum, we will now introduce the dynamics of the pendulum by introducing a potential force. The potential force that we're interested in, of course, is gravity. Gravity in the Cartesian world looks like a constant accelerator. So gravity adds 9.8 meters per second squared acceleration, and you can see that we now have a new differential equation in theta. It looks a little bit like the chi double dot equation that we had before in the previous segment on linear time invariant 1 degree of freedom particle dynamics. But now we've got the nonlinear term sine theta, which is a consequence of the nonlinearity introduced through the kinematics. Well, we could agonize about solving this differential equation. We're given the dynamics, ml squared theta double dot equals this right-hand side function sine theta. But we'll find that the mathematicians have discovered a while ago that these nonlinear systems cannot be solved in closed form the way the linear systems can be solved in closed form. Fortunately, the energy dynamical systems point of view that we took in the previous slide, where we thought about the energy in a norm-like fashion, those ideas do generalize, and we will proceed to use those ideas here. Well, how can we repeat the analysis of the linear case in this nonlinear setting? Let's remember what we did. We realized that there was a chi dot plane. Here we're going to realize that there is a theta dot plane. Namely, what we will do is we will assign to Q1 the variable theta, and we will assign to Q2 the variable theta dot. Please keep in mind that Q, the phase variable, is two-dimensional for a very, very different reason than P. P is the Cartesian position of the point mass. Really, this point mass is constrained to have just 1 degree of freedom, theta. So we are looking now with the variable Q at the phase space of theta. Namely, Q has coordinates position and velocity, even though, unlike the old vector x in the previous segment, the vector Q lives in a nonlinear space. We can write down a first-order differential equation in Q the same way that we wrote down the first-order differential equation in x in the previous segment. Namely, Q1 dot d by dt of theta is theta dot, which is just the second derivative and second position Q2. In Q2 dot, we realize Q2 dot is d by dt of Q1. So d by dt of Q1 is Q1 double dot, and Q1 double dot means that we should solve for theta double dot in this scalar second order physical version of this first order two-dimensional system that we're writing down. The mathematicians understand enough about equation 5 that they can promise us that every initial condition still has a good trajectory that I'm denoting Q of t through the initial condition Q0. But unlike the original equation of the linear time invariant case, Qt is not available in closed form. Let's push on. Instead, let's try to use an energy conservation argument to deduce the asymptotic properties of Q of t over time. Let me write down again eta sub sp, the total energy of the simple pendulum. Now I'm going to write down the kinetic energy of the pendulum, which depends only on the velocity Q2, together with the potential energy due to gravity, which depends only on the angle position Q1. I once again must do the power calculation that I tried to do and succeeded in the linear case. Namely, I would like to show that with no dissipation at all, Hamilton was correct and the total energy is conserved. Let's do that computation. Let's show that d by dt of eta, when eta is composed along the motions of this system, that d by dt of eta is always 0, so that eta is constant. I'm going to write down in theta and theta dot coordinates, and then rewrite them in Q1, Q2 coordinates to get the expression for eta as a function of Q at any time t. I'm going to realize that because of conservation, if it's true, then I can rewrite Q, either Q1 or Q2, let's say rewrite Q2 as a function of Q1, and now I'm plotting on the Q1, Q2 plane in red the function Q2 of Q1 that we get by assuming that the total energy is conserved. If we add damping, it will turn out that there's a viscous term, and our d by dt computation of total energy will reveal what Lord Kelvin realized, which is that the total energy is no longer conserved, but must be decaying down to 0. These computations are not hard to do, but they will take some time, and we provide exercises for you to work on them if you care to in a supplementary material to this lecture. Let's now pass on, assuming that these derivations are correct, and interpret the change of energy, the negative change of energy, as a basin-like property. Namely, we're going to look at two different trajectories. We're going to look at the trajectory around the fixed point at the bottom and the fixed point at the top. What do I mean by a fixed point? I mean what you know physically, that if you position the pendulum in the Earth's gravitational field with no velocity, with the pendulum pointing straight down, it will stay there forever. Similarly, if you position the pendulum straight up with no velocity and you balance it exactly right, you know intuitively that it will also stay there forever. But you also intuitively know that these two different fixed points or fixed positions of the pendulum have very, very, very different behaviors. If you position the pendulum underneath, down under, it will stay there forever, and if you bump it, it will at least oscillate, and if there's damping, it will oscillate back down to the 0, 0, no energy position. In contrast, if you start with the pendulum pointing exactly up at the fixed point, and you bump it a little bit, whether or not there's damping, this pendulum will escape from its top position, and it'll continue to oscillate forever if there's no damping, or it will die down to the bottom under fixed point asymptotically. In either case, the top behavior is unstable. The bottom behavior is stable. And we must now develop a mathematical way of thinking about and analyzing and talking about such different circumstances. Let's look at the behavior down under, a stable fixed point. The equilibrium motion, or the fixed point motion, is constant over time. Namely, if I start at theta equals 0 and theta dot equals 0, I'll stay there forever. The pendulum at the top, where theta is equal to pi and theta dot is equal to 0, is also a fixed point, but we'll show it's unstable. First, let's define what we mean by stability. Stability is the notion that motions that start close together should stay close together. Asymptotic stability, which is even more important to us, adds the notion that motions that start close together not only stay close together, but actually come asymptotically closer and closer until they converge. You know intuitively that this is just what's going to happen to the damped pendulum. You know that if you knock it a little bit off its bottom fixed point, that it'll oscillate a little bit and settle down to the 0, 0, 0 energy state. We would like to use energy methods to show that this is true mathematically. Let's look at the pendulum near the bottom, and we'll see that its total energy gives us a norm-like shaped curve. There are closed circles close to the bottom when we express total energy level curves. And since the power is non-positive, we know that we're going to get a red, yellow, blue picture in the nonlinear setting, just like what we got in the linear case. In the linear case, these red curves were analytically determined. In this case, these red curves are developed by numerical simulation, and they're not closed form, but mathematically we know that they must be converging for the exact same arguments that we used before. We conclude that the bottom fixed point has asymptotic stability. And we've never needed to solve for the motions because we showed that the total energy is decreasing. That idea is summarized in this total energy basin picture, where you see the red motions in the phase plane, Q1, Q2 phase plane below, and projected up onto the energy surface as blue ghost curves, showing that all the energy is being sucked out of any of these initial conditions by the viscous damping of the pendulum shaft. In contrast, let's go to the unstable fixed point at the top and do the same computation. The power is still non-positive. d by dt of eta is still negative. So the power is still non-positive, and so the energy must be decreasing. But let's see what that means. If we plot the level curves of the total energy function near the top, where theta dot is equal to 0, but theta is equal to pi, then we see that our level curves are saddle-like. And indeed, when we plot numerically in red the solution trajectories over time, we see that energy indeed is decreasing, but it's decreasing by running down in one direction and then running down further in the other direction till we get bluer and bluer and bluer. So energy dissipation in this case does not imply convergence. Around the unstable fixed point, the total energy is not norm-like, and therefore its decay does not tell us anything about stability, and in fact enables us to deduce instability. We conclude that it's lonely at the top, It's unstable at the top. And we show this again by thinking about the total energy surface as a saddle in space, where the red motions over time are being projected into these blue ghost curves on the energy surface, and we can see that running down the saddle doesn't mean that you're going to run to the point of the saddle. It means that you're going to run near the point and run off the saddle all the way down to the stable fixed point below. We can do this without ever computing the solutions. I find it convenient to illustrate what's going on with these red numerically computed trajectories, but the blue story is all you need mathematically to conclude that this fixed point is unstable and the fixed point below is stable. The total energy basin defines a task. We're going to think about these energy basins as task symbols, and we're going to try to start composing these task symbols later on in this series of lectures. The basin properties were established rigorously only in the late 20th century. These are greedy, tireless efforts of the physical system to get to the bottom of the local fixed point, and we're going to try always to encode what we want out of our robots in these very robust terms, because we don't need to know that much about the initial conditions, we don't need to know that much about the details of the friction. All we need to know is that the friction, or whatever energetic method, is pulling the energy away from the fixed points we don't like toward the fixed points that we do like. Best yet, these properties are persistent in that we don't need to know exactly what the masses are or exactly what the spring constants are. These properties will still persist under perturbations in the parameters. So the notion of dynamical task encoding, ideas that I began to think about 20 or 30 years ago, have lasted and generalized and enable us to begin to implement more and more complicated behavior using artificial potential energy landscape functions. These ideas we're going to try to convey to you more intuitively as the segments go along, but we included this more mathematical rendition in the simple 1 degree of freedom case so that you could, if you wanted to, make the connection between the intuitive ideas that we're presenting later and the mathematics that underpins them, and introduce those ideas to your future study goals.